Hello, and welcome back to Lecture 6 of the Foundations in Kinematic Analysis lecture series. In the previous lecture, you learned how to pre-process your raw motion tracking data to get it ready for analysis. However, when we study multimodal language, we are often bringing together data from multiple information sources. For example, we might want to analyze motion tracking data from gesture, audio information from speech, or gaze data from eye tracking. Today we'll show you how to merge your motion tracking data with other data streams so that we have all of our data in one place. One source of data that we'll be dealing with in this lecture series is ELAN annotations. These annotations are time-stamped, indicating when an event of interest occurred. In this example, I've highlighted a gesture stroke annotation. On the left side, you see the names of 4 tiers, and these are different layers of information that we've annotated. In our dataset, we have an ELAN tier called word that segments the individual words that participants said. These annotations were segmented using automatic speech recognition from WhisperAI. Then we have a tier called gesture unit that identifies segments of the videos where the speaker was actively gesturing. A gesture unit annotation starts when the speaker lifts their hands from a resting position and ends when they return to a resting position. A single gesture unit can contain multiple strokes if the speaker produces a series of gestures in a row. Then underneath that, we have a tier for individual gesture strokes. A gesture stroke corresponds to the core meaningful movement within a gesture. This is the part of the gesture that conveys the primary semantic or pragmatic meaning, and it is often the most kinematically salient movement. In this 45-second video, the speaker produced 22 gesture strokes nested within 6 gesture units. And finally, we have a tier called hand that is a dependent tier on the stroke tier. And this indicates whether the gesture was produced by the right hand only, the left hand only, or both hands. We want to link this information to our motion tracking data so that we can analyze the kinematics of individual gesture strokes and perform those calculations based on which hands were involved in the gesture. These gesture units, strokes, and hand annotations were done manually, but you may also consider ways to automatically segment or classify this information. In the description below, I'll link to resources for getting started with ELAN, for getting automatic speech transcriptions from Whisper, and some examples of automatic gesture segmentation models. When working in ELAN, you can export your annotations into a text or CSV file. For this tutorial, we will only import annotations from the gesture tiers, so we will deselect word. For output options, you want to deselect the separate column for each tier option. And then for the time settings, we want to include columns for begin time and end time in the format of milliseconds. So if you open your CSV file, you'll see something that looks like this. Each row corresponds to a single annotation and indicates its begin and end time in milliseconds. For example, we can see that the first gesture unit annotation is about 4.5 seconds long, beginning at 16 milliseconds and ending around 4,600 milliseconds. So this is what our ELAN data look like after we've exported it. Another type of data we'll be working with, specifically in Lecture 8, is the audio signal of participants' spoken language. When people speak, the amplitude or intensity of their voice changes over time, which is visible by the height of the audio waveform that you see here. Speech amplitude corresponds to how loud we perceive the speech to be. A speech amplitude envelope shows the overall shape or outline of the speaker's volume. The audio signal is averaged over short time windows to create a smoothed amplitude envelope. This smooth speech amplitude envelope is the data we will use in our analysis. So our speech amplitude signal looks something like this. This is what the corresponding data frame for the speech amplitude envelope looks like. Each row corresponds to how intense the speech signal was at a given moment in time. In Lecture 8, we'll use this data to look at how changes in the speaker's loudness correspond to changes in gesture velocity, which we refer to as speech-gesture synchrony. We'll come back to that later. For now, our goal is to get all of our data in one place so that we can analyze it together. So now we're working with 3 data streams. We have motion tracking data, speech amplitude data, and ELAN annotations. So we'll start with motion tracking and speech amplitude. These data frames are structured pretty similarly. We have a column called time, and then additional columns for our continuous variables. But you'll notice that the values in each of the time columns increase at different increments. This is related to their sampling rates. Our motion tracking data has a sampling rate of 30 Hertz, meaning we have 30 data points per second, or a new data point about every 33 milliseconds. In contrast, the speech amplitude has a higher sampling rate of 100 Hertz, meaning we have 100 data points per second. If we merge these 2 time series together, we see that their times don't line up. For example, we don't know the position of the right wrist at 10 milliseconds, and similarly, we don't know the speech amplitude at 33 milliseconds. This means we end up with a lot of missing data, particularly in the motion tracking columns. To solve this problem, we can use linear interpolation to fill in the missing values. In this plot, the 3 points represent our known values for the x position of the right wrist at 0, 33, and 67 milliseconds. When we use linear interpolation, we draw a straight line between known values. For example, we assume that the position of the right wrist at 20 milliseconds falls in between its position at 0 and 33 milliseconds. This process is called upsampling because we are increasing the sampling rate of our motion tracking data so that it matches our speech amplitude data. We can now drop the rows where speech amplitude values were missing so that our time column increases at equal intervals again. Now, both our motion tracking data and our speech amplitude data have a sampling rate of 100 Hertz. In general, when you have 2 signals with different sampling rates, the best strategy depends on the kind of analysis you want to perform. If the sampling rates are relatively similar, it is often preferable to upsample the lower rate signal rather than downsample the higher rate one. This is because downsampling can lose information and reduce the resolution of the signal. However, in phonetics, audio signals are often sampled at much higher rates, for example, at 48 kilohertz. This is much higher than the motion tracking data that we typically work with, and it would not be appropriate to resample the motion tracking data to such a high rate. If you're interested in slower temporal patterns, such as amplitude envelopes or articulatory movements, you'd want to choose a common sampling rate that preserves the relevant features for your analysis. Our last step is to load in our ELAN annotations. In the highlighted row in the table on the left, we have a hypothetical example of a gesture stroke that starts at 16 milliseconds and ends at 133 milliseconds. If you look at the table on the right, I've also highlighted the rows in our motion tracking data frame where the values in the time column fall between the begin and end time of our gesture stroke. In our Jupyter Notebook tutorial, we will use a function that loads in our ELAN annotation values by checking whether the time point for a given row falls within one of the time annotation windows. So we end up with something like this, where we have a column indicating whether a gesture stroke was occurring at a given moment in time, and the highlighted rows correspond to the wrist position of a single gesture event over time. This is the final form of our data set. Now that we know when gesture strokes occurred, we can analyze movement kinematics for gesture strokes in our data set. For example, we could calculate the maximum wrist velocity for a given gesture stroke. The process of merging different data streams is also described in this research article, which we'll link to in the description below. Although this lecture series focuses on motion tracking, speech amplitude, and ELAN annotations, there may be other time series data that you want to merge with your motion tracking data. For example, this paper uses speech fundamental frequency, which is related to voice pitch. You might also have eye tracking data or other physiological measures like muscle activity. The principles you learned in this lecture apply to any time series data. Now it's time for you to practice merging data streams using our toy dataset. Join me now for our Jupyter Notebook tutorial. Let's navigate to the Lecture 6 script folder. Usually inside the script subfolders, we only have the Jupyter Notebook file and an output folder, but there are a couple other components in this one. We have a CSV file called participant metadata. Let's open that up. This is a very small file, but in research studies, we often have a key file that contains information like the participant ID number, and maybe some sort of experimental condition that we've assigned them to. This is meant to mimic that. So for example, you can see that the 8 participants are assigned to a group called either pattern or no pattern. This is just a silly example, but it refers to the clothing that they are wearing. So whether they are wearing a solid color or have patterns on their clothes. We also have a folder called ELAN files. The actual ELAN files themselves have the extension .eaf. If you open one, it looks something like this. And then you'll see we have a CSV file called KLS ELAN. This is the data I exported from the ELAN files. So for each participant file, I have a list of all of their gesture stroke annotations with the beginning and end timestamps. This is how we know when gesture events occurred in the videos. We want to link these annotations to the motion tracking data. Okay, let's open the Jupyter Notebook. Select your kernel and activate the KLS environment. This notebook has 4 sections. First, we'll set up our workplace, then we'll extract the speech amplitude envelope from audio files, then we'll merge the motion tracking and speech amplitude data together, and in the final step, we'll load in our ELAN annotations. Starting with section 1, as usual, we will run this cell to import the required Python packages. And we're also defining the path to different data files that we'll use in this notebook. This includes the location of our cleaned, pre-processed motion tracking data that we saved in the previous tutorial, the CSV file that contains the participant key or metadata, and the CSV file containing the ELAN annotations. In this next cell, we will read in each of these 3 data frames. We are giving them each a short name, MT for motion tracking, key for the participant data, and anno for the ELAN annotations. So run this one, and in the output below, you will see a preview of each one, showing the first few rows of each dataset. Okay, moving on to section 2. Let's extract the speech amplitude envelope from our video files. First, we're going to define 3 helper functions. The first one, called extract audio from video, is used to create audio wave files from our video files. The second one, amplitude envelope extract, calculates the speech amplitude envelope from the audio files. And the last one helps us to organize the speech amplitude data into a data frame that we can merge with our motion tracking data. Run this cell. Now we will use the functions we just defined. First, we will extract the wave files. We are defining the path to the input videos and the output folder for Lecture 6, where we will save the audio files. It will process different kinds of video files and export them as wave files. This code is looping through all videos in our input folder, so go ahead and run this cell. You might notice that you got some output messages that say it found 8 videos to process, but it skipped them because the audio files already exist. This is because the repository you downloaded from GitHub already has the audio files. This prevents us from wasting time by reprocessing them. But let's go ahead and go back to the course folder and manually delete them from the audio extraction folder. Now, when we rerun this cell, it will process the videos and save them to our folder. Now that we have our audio files, the next step is to extract the speech amplitude information. This time we're setting up paths for where the audio files are that we just created, and a new output folder where we'll store the CSV files containing the amplitude envelope data. Like before, I'm going to go back to the course folder real quick and delete the old versions of the CSV files so that it generates new ones when I run the code. Otherwise, it will skip it again. In this function, we're using a technique called the Hilbert transform to estimate the amplitude envelope. We set a couple of parameters, including a smoothing window of 5 Hz and an output sampling rate of 100 Hz. This means that in the output CSV file, we have a new data row every 10 milliseconds. Go ahead and run this cell to loop through our audio files and generate the speech amplitude CSV files. Now that that's complete, let's visualize what the speech amplitude data look like. Let's run this cell. Here we are plotting 2 graphs. In the top graph, we are visualizing the original waveform of the first audio wave file. Then we are reading in the corresponding speech amplitude CSV file for that audio file and plotting it below. We've zoomed in a bit, showing only the first 15 seconds. You can see how the amplitude envelope in orange follows the overall change in speech loudness, but smooths over the tiny fluctuations in the raw waveform. The goal of section 3 is to merge our motion tracking and speech amplitude data together. Right now, we have separate speech amplitude CSV files for each video. The first thing we're going to do is concatenate those CSV files into one data frame. We will loop through all of our CSV files in the output folder and create a new column for each one called video that matches the file name, and then combine them into one file. You can run this now, and then in the output you will see a preview of the combined speech amplitude data frame. Time increases by 10 milliseconds, and then we have a column for our amplitude and video. Let's go ahead and run the next cell. In this code, we take our motion tracking data frame and our speech amplitude data frame and merge them together based on the values of the time and video columns that they have in common. But when you preview the merged data frame below, you'll notice that we have a lot of missing motion tracking data. And our time column does not increase at equal intervals because the motion tracking is sampled at 30 Hz and the amplitude data is sampled at 100 Hz. To solve this issue, we're going to upsample the motion tracking data to 100 Hz. We are setting up this function to use linear interpolation to upsample only the motion tracking columns between existing data points. Then we will drop the rows where there are any NAs in the speech amplitude column. These are the rows that correspond to the original motion tracking rows at 30 Hz. Then, because linear interpolation draws straight lines between known data points, it introduces very small corners in the motion signal. So we're also applying a Butterworth smoothing filter to get rid of these small artificial fluctuations. If you look above, you can see that I put in the same cutoff frequency that I used in the previous tutorial, which is 3.34 Hz. You can adjust this if needed. Let's run this cell and create a new data frame called merged_clean, where we will apply the upsampling and smoothing. Now, when we look at the preview, we can see that time increases by 10 milliseconds. We don't have any NAs in our motion tracking columns, and if we scroll to the right, we also have all of our speech amplitude data. Now that our motion tracking and speech data are aligned, we can add in our participant information. Here, we're merging our upsampled data frame with our participant key file. Go ahead and run this. Then in the output, you will see that we have our identifying columns for participant ID, video, and what group they belong to, pattern or no pattern. We will use this information to help us visualize group differences in later tutorials. Let's take a moment to visualize our motion tracking and speech amplitude data together. We are creating two plots. The first one is looking at amplitude on the y-axis, and the second one is visualizing the x and y position of the right wrist. You can run this now, and now we can see how both of these signals change over time. In Lecture 8, we will look at individual gesture strokes and compare whether gesture speed peaks correspond to peaks in amplitude to better understand how these signals pattern together. But for now, we're just happy to have all the data in one place. But there's one more piece of data that we're missing. In the next section, we will load in our ELAN annotations, which tell us when gesture strokes occurred. Our ELAN annotation file has a separate row for each annotation, but we have data from multiple tiers, and we want to separate these out. So to start, I'm creating 3 small subset data frames based on the value in the tier column. So we'll create a separate data frame for gesture units, gesture strokes, and our handedness annotations. We are also creating a unique numerical ID for each gesture unit and stroke. Our motion tracking data is continuous, so having a numerical ID for each gesture stroke helps us know where one stroke ends and another begins, so that we can analyze the kinematic properties within individual strokes. You can run this code, and at the bottom you'll see previews of these 3 subset data frames where we have the begin and end times for each annotation for gesture unit, stroke, and hand annotations. This next code chunk is reading in an image from our screenshots folder, showing a reminder of what the stroke annotation looks like in ELAN versus how we want it to appear in our motion tracking data frame. The main function we're defining is called loadInEvent. To use this function, we will specify the motion tracking time column, the motion tracking video name column, the annotation data frame that we want to get annotations from, and the name of the column we want it to map the values from. This function looks at each time point in our motion tracking data frame and checks whether it falls inside an annotated event for that video file. If it does, it adds the value from the annotation column name. So let's run this. And now in this next cell, we will apply this function. The data frame that we are working with from above is called merged2, and you can see that we are adding 5 new columns: gesture unit ID, stroke, stroke ID, and hand. We are reading these annotations in from the corresponding annotation subset data frame and column. Run this now, And in the output, I'm previewing the first 150 rows because not all motion tracking rows correspond to gesture events. If we scroll to the right, we can see that at the beginning of the video, there is no ELAN annotation data, but starting from around frame 146, we do have annotations for the first gesture unit and gesture stroke of this video, and it says it was a right-handed gesture. Now that we know when gesture events occurred, we can visualize those segments of motion tracking data. In this code cell, we are creating a plot to visualize the motion tracking data of the first gesture unit for one of our participant videos, which we defined at the top. We are plotting the speech amplitude and the X and Y right wrist position. Let's run this now. And now we can see what these signals look like for the first gesture unit produced by this participant. You can also experiment with different participants or gesture IDs. I'll change the gesture unit ID to 2 and then run it again. Now that everything is in one place, the last step is to save the merged data into a CSV file so that we can analyze it in the next lecture tutorial. You can run this now and save it to our output folder. Let's go back to our course folder and see how it looks. This one is called mergedData.csv. We have our participant metadata, our motion tracking columns, our speech amplitude columns, and ELAN annotations. At the beginning, these are blank, but if we scroll down, we'll see that the first gesture unit starts. And gesture units start with a preparation movement, so we need to scroll further down to eventually see the start of the first stroke. And that's it for this Jupyter Notebook tutorial. Of course, you can also analyze motion tracking data independently without considering speech amplitude envelope or ELAN annotations. But if you do have multiple different forms of data that you're interested in analyzing together, we hope that this gives you some helpful tips for how to bring these data streams together. In this lecture, you learned how to merge all of our data streams into one place and how to deal with data that have different sampling rates or formats. In the next lecture, we'll show you how to convert the position data that we have into measures of speed and velocity so that we can see not only where a participant's wrist is at a given moment in time, but also how fast it's moving. Thanks for following this lecture series, and we'll see you next time.